Something's happening. Looks like it's working, right? Okay. Today we'll cover out-of-order execution. It's a topic you've been waiting for, probably. Yeah, finally. Good. Hopefully you learned everything about virtual memory. Maybe not everything, but a lot of things about virtual memory in the last 2 lectures, right? Okay, that's a very important concept, and as I said, that's one of the most successful hardware-software cooperative concepts that has made programmers' lives so much easier because they don't need to manage memory. At least they don't need to deal with limited size memory. They still run out of virtual memory, that's another problem. But you don't need to worry about physical memory. You might have gotten errors like running out of virtual memory, right? Out of virtual memory. Has anyone seen that? Yes.
Yes.
Yes, it's painful, right? That's because you don't have enough address space in your virtual memory, right? If you have a 32-bit processor, you have a 4 gigabyte address space if it's byte addressable. Okay? Okay. Well, we'll cover some things about virtual memory later on, so I'll keep the concepts that you have. Well, keep them forever, because those are good concepts. It's a good example of indirection also, right? It enables. And a level of indirection buys you a lot. It hides you, it gives you the ability to give the illusion to the programmer that something is infinite. Well, not infinite, but something is much larger than it is. And also it enables you to do tricks like address translation, demand paging, and also it enables you to do protection. So hopefully you've covered all of those concepts. Well, today we'll cover out-of-order execution. That was, virtual memory was like a hump in the middle. So we'll talk about how to enhance pipeline performance a little bit more. This is dynamic instruction scheduling. But a few announcements. Hopefully you know that the lab's due Friday. If you don't know, then you may be in trouble. Has anyone finished the lab? Yes? No? Not yet? Is it hard?
It's fun.
It's fun. Okay, I like that actually. It's fun is a good good thing. It could be hard, but it's fun. And don't forget the extra credit. Extra credit is actually a competition this time. Yes?
So for the extra credit, the thing says that your lab has to be 100% correct.
Mm-hmm.
But it's kind of hard for us to know that because like I know like I wrote some tests for my previous lab and it seemed to pass but it didn't, and some people wrote some even more extensive tests and it didn't pass your test but it passed their test. Okay. So it's kind of hard for us to know how to submit it, or if you see what I'm saying.
I didn't do your best to get it correct.
Okay.
Well, we may change.
Okay.
If no lab is correct, for example. But whenever you design something, the first goal is correctness, right?
Yes.
If it doesn't work, then performance doesn't matter. That's why the handout says so. Mm-hmm. But if no one gets it correct, then we'll adjust based on the test. Maybe no one gets the extra credit.
No, because some of the tests involve the critical path, and if you get it incorrectly, you might shorten that critical path.
That makes sense.
That's right, exactly. So if you can make something incorrect, then you can speed up something by infinite.
I guess my question is, maybe now it's too late, but would it be possible for us to get some like test that tells you whether you're correct or not, but it doesn't tell you what specific thing is wrong?
Oh, I see.
So it doesn't give us too much information, but it'll let us know when we're good.
When you're incorrect.
Yeah, when you're incorrect.
Well, I'll let Rachada ponder that for a while. Let's talk about it today.
It might be too late. It's okay.
Yeah, maybe a bit later.
No, we failed.
But actually, I have a slide covering that.
Oh, okay.
We'll get back to that. Not exactly that, but about testing your code. Okay, this is a real life problem. You know, when Intel designs processors, it doesn't work. You cannot sell it as 4 gigahertz, right? It doesn't work. That's the exact same problem you're facing now.
Yes.
So try to get it correct. It's fun, as you said. Okay, homework is due next Wednesday, and then there's an exam coming up before spring break. This is just that's 2 weeks from now, right? Oh, semester is moving quickly. I wanted to remind you, some of you may not have attended, but you have actually 7 days now for total late days. And you can submit your lab. Each late day beyond all exhausted late days costs you 15% of the full credit of the lab. Okay? So I'd like you to submit the labs. In order to testing your code, basically testing is critical in any deployed system, right? Or in developing any system, or deploying any system. And you're responsible for creating your own test case and ensuring your test designs actually work for all possible cases. So I anticipated your question, maybe. But basically, that's what we expect. Now, it's true that even existing processors have errata. We've discussed this briefly. Maybe there are some corner cases they don't get correctly, but almost all cases they get working correctly. At least ISA, satisfying the ISA. That's how real life also works. Basically, no one gives you all possible test cases, workloads, users, etc. beforehand. So somebody has to design such that that interface is obeyed, right? That's why I think it's important to not give you all possible test cases that we have. And it makes it more fun. Okay, having said that, this is the Lab 2 grade distribution. These are all online, so I'm not going to spend a lot of time on this. You can find, well, it's not online yet, maybe, right?
It will be online.
It will be online, yes. Yeah, all of the grade distribution will be online. And I don't know what happened here, but if you're around here, you should really talk with the TAs and figure out what happened. It may be something simple, it may be something disastrous. Okay? And I'm glad to see this part. This is actually, I would like to push this distribution over here as we move forward. Okay? Then you can look at the statistics and get a good idea of where you are, how you're doing on the labs. But I'd like everyone to be around here, and it's possible actually to do that. Okay? And this is the homework grade distribution. This is a little bit better because we don't have a big hump over here. And this is good. But homeworks are, as I said, it's more for your benefit, right? To prepare for the exams. Still get 100 on those. Okay? Okay. I think I've shown this slide many times. I'm not going to show this again. Hopefully this will be the last lecture. Maybe last lecture, and we'll have 1.25 lectures on these topics. But for today, we're going to cover mainly out-of-order execution, which is actually covered in this reading. And hopefully you've done that reading by now. How many of you have done it? I'm proud. You can raise your hand high. Okay, good. How many of you will do it? Okay, good. How many of you never plan to do it? Okay, good. You shouldn't raise your hand here. Okay, but definitely do this reading. We're going to cover the concepts in detail today. And this will put everything together, everything we've covered together. And there will be some advanced concepts over here. For example, one example, we've covered branch prediction, right? The Alpha 21264 has a branch predictor, but it also has something else called the line predictor, next line predictor, or next cache block predictor. So it not only predicts branches, but it also predicts which cache block will you be fetching from next in the instruction cache. This is because it's a superscalar processor, and it needs to fetch multiple instructions per cycle, and any of them can be branches. And the next address resides in some cache block. It could be the same cache block. And what they try to do is, if you fetch this cache block, what is the next cache block you're going to fetch from? Such that you can supply the next n instructions, where n is equal to 4 for this processor. So you'll read about something called a line predictor. And that's the purpose, again, to make the fetch quicker. Because you need to predict the next line quicker. Maybe not all of the individual branches within a line, but the next line. When you have the next line, you can figure out where the branches go. You can do the individual branch predictions. Okay. So existing processors are actually much more complicated than what we've discussed. And this will give you a good idea of what an existing, but it still has the fundamental concepts that we covered. Today's processors are not too much different from Alpha 21264 conceptually. Implementation-wise, they're much, much more power efficient. They do a lot of tricks to get the power down. This was I don't remember the power budget for this one, but it was pretty high for the time. Okay, for next lecture, actually next few lectures, we're gonna switch gears a little bit. We've been covering we've been covering single instruction stream, the von Neumann model, but we'll also look at now more parallel models, other models, like SIMD processing, single instruction multiple data processing. And we'll talk about basic GPU architecture. And we'll also go into other execution models like VLIW, data flow, and systolic arrays. So the next few lectures, after today's lecture, will be hopefully interesting too. Okay, and these are the readings for the next lecture. Okay, just to give you a reminder, we talked about maintaining precise state. I'll briefly cover this and finish this. There were 4 methods of doing this: reorder buffer, history buffer, future register file, checkpointing. And existing processors actually employ the future register file. They do employ some sort of checkpointing, and they do employ the reorder buffer, because future register file requires a reorder buffer, if you remember. And keep this in mind, this is to maintain precise state. This is also applicable to out-of-order execution, because in out-of-order execution, the problem is the same. You need to reorder the instructions somehow and maintain a precise state. So all of these solutions apply to out-of-order execution, and they need to be modified slightly. But hopefully you know all of this. We'll come back to this at the end of out-of-order execution, but I'll talk about registers versus memory. In all of these topics, if you remember, we talked about maintaining precise state in the register file, right? We didn't talk about memory at all. You can think of memory as a huge register file, but it's nearly not like that, right? Because register addresses are allocated by the compiler and they're known, whereas memory addresses are not known, not all of them at least, by the compiler, because some of the memory is dynamically allocated, right? You do malloc and you get the memory address, and compiler has no idea what that memory address would be. Compiler even doesn't know whether one node is accessing a memory address that another store is accessing, right? If you have dynamically allocated memory. So that's one of the differences between registers versus memory. We'll get back to this, but memory is part of the architectural state as well, and that needs to be preserved as well. It should be part of the precise state, right? And there are 3 fundamental differences between registers and memory. I'll give these to you, and maybe I'll ask them when we get to it. Actually, we've talked about this before, right? Register dependencies are known statically. Compiler allocates the registers, right? Whereas memory dependencies are determined dynamically, especially if you have dynamic memory allocation. If compiler allocated all memory, then these would be exactly the same. But that doesn't happen in most existing systems. Well, this is kind of obvious, right? Register state is small, that's why it's fast. Its register file is fast. And memory state is much larger. And this is another difference. Register state is not visible, at least in existing systems, to other threads and processors. Whereas memory state in a shared memory multiprocessor is shared between different threads and processors. So if you actually are imprecise, if you commit a value, write a value to memory, speculatively, then you have a problem, right? Because some other thread can grab that value and do something with it. And that may cause a problem, because if you shouldn't have committed that value to memory, then you could get an incorrect result. And we will see this actually. We will see this when we cover memory consistency and memory coherence later on. But think about this. How do you actually maintain precise state in the presence of these requirements? For example, if you have a history buffer, remember the history buffer? You read the old register value, and then you commit the value that you're writing for this instruction. If something happens, something bad happens, some exception happens, you undo what you've done. That could be done with the register file, but it's very difficult to do something like that with memory, right? Because if you actually commit a value that you shouldn't have committed, somebody else, some other thread might read that value, and undoing that operation now becomes a lot more complex, right? It's not simply changing that memory location to its old value. You somehow need to inform all of the threads that have read that memory location that they read the wrong value, and you need to supply that correct value to them. So it becomes a lot more difficult to handle memory if you handle memory correctly, memory correctness, if you commit a value that you shouldn't have committed. So some operations, some solutions to the precise state problem become very difficult with memory. History buffer, for example. So what do most processors do? Well, this is what we discussed actually just now. Basically undoing a memory write is much more difficult than undoing a register write, because memory is visible to other processors. Well, what many processors today do, and we'll get back to this at the end of out-of-order execution, is what they do is they keep store address and data in the reorder buffer. So basically, the reorder buffer keeps all of the stores as well, but it keeps all the instructions, so why not keep the stores and addresses and data? And then load instructions search this buffer to find their data. If you're doing a load, basically, you need to search this buffer. Because now, if you remember, for register operations, the data could come from the register file, reorder buffer, or the bypass paths, right? I'll call this the forwarding paths. Similarly, for memory operations, the data can actually come from the data cache, or data memory, let's say. And it could come from the reorder buffer, because there may be some store operation over here that is not finished yet, that has not written its value to data cache, but has its address and data ready, but it cannot complete because it's not the oldest instruction in the machine. Right? Remember, we want to complete instructions in order. So if a load is executed over here, it needs to search this reorder buffer. If the data, if its address actually exists in the reorder buffer and a store is writing to that address, then it can get the data from the reorder buffer. Does that make sense? That happens if you have outstanding stores that are before the load in the reorder buffer. Okay, we'll get back to this because this is actually a complicated part of the machine. So people have actually simplified this because if you may have a reorder buffer that's much larger than the number of stores that you support in the machine. If you have a, let's say, 126 entry reorder buffer, just like Pentium 4 had, you may not want to do the search, right? Because the search is actually expensive. And we'll get back to this. We'll talk about how expensive the search is. So start thinking about it. Basically, what is the search? Basically, you're searching this address in all of the entries, all 126 entries of the reorder buffer. It's basically a comparator per entry, right? And the address could be pretty large. Let's say it's a 32-bit address. It's 126 32-bit comparators. It's, again, a content addressable memory. But it's much worse than the content addressable memory for registers. Because a register ID is 6 bits or so. This is 32 bits. It's actually much worse than that because you can have partial overlap in the address, right? Maybe you have a store over here writing to 1 byte, and you have a load that's reading 32 bits or 4 bytes. You need to figure out that overlap. So it's actually a range match. So it's a complicated circuit. So think about it for now. Basically, what turn processors do is they have a store or write buffer that contains store operations in order, and that contains only store operations in order. Whenever you have a load instruction, it searches this store write buffer to get its data. That simplifies the search a little bit because now you don't search this huge reorder buffer because reorder buffer contains all of the instructions in the machine that are decoded but not yet retired. You search a smaller buffer. Make sense? So when you read the alpha 21264, you will see that it has a, how many entries? I think it has a 24 entry store buffer. I may be wrong about that. But it's much smaller than the 80 entry reorder buffer they have. Okay, basically this is a program ordered list of uncommitted store operations. And when a store is decoded, it's very similar to a reorder buffer, right? When an instruction is decoded, in this case, when a store is decoded, you allocate an entry in the store buffer. And then when store address and data become available, you record the address and the data in the store buffer entry for that store. And when the store becomes the oldest instruction, then you take oldest instruction in the pipeline. It's not the oldest store, right? It should be the oldest instruction in the pipeline. You update the memory address with the store data. Okay? You take the address and you write the data to that address, basically. That's how you commit memory operations in order. But at the same time, you can forward data from these operations that are outstanding by doing the search. Make sense? Okay. Any questions on this? Again, as I said, we'll get back to this because this is actually one of the most sophisticated parts of an out-of-order execution engine today. And it's one of the most difficult to scale parts as well. How do you do this load store forwarding through memory? Exactly because of these three differences between registers and memory. Handling memory is much more difficult. Okay, but let's handle registers first to enable out-of-order execution. I guess it's a good way to go into out-of-order execution, saying that memory is harder. But let's first handle the registers. Okay, we'll talk about out-of-order execution. This is dynamic. It's called dynamic instruction scheduling because you dynamically determine the order of instructions that are dispatched into functional units. Remember, in an in-order machine, the order is program order, right? Instructions are scheduled in program order. You dispatch in program order. So a compiler can do the scheduling. It's called static instruction scheduling. Let's do it dynamically. Well, what's the problem? Why do we want to do something like this? We've already discussed this, actually, so I'm going to go through this relatively quickly. The problem is if you have an in-order pipeline, whenever you have a true data dependency, you cannot dispatch a younger instruction to functional units. Remember, if you have an in-order pipeline with a reorder buffer, if you don't have a true data dependency, a false data dependency, you could actually dispatch the instruction because the reorder buffer renames the registers, right? We've discussed this. But if you have a true data dependency, you have to stall because this instruction that's being decoded needs a value that's to be produced later by one of these instructions in the pipeline. And if you move this forward, you can get incorrect results. And we've already discussed what a dispatch is. Dispatch is the act of sending an instruction to a functional unit. So you cannot send an instruction to a functional unit if it's dependent on one of the instructions that are being executed over here. So let's take a look at two cases. Well, let's take a look at this case first over here. I show you two pieces of code, a multiply writing to register 3, and an add reading from register 3. And a bunch of adds over here. A load writing to register 3, and an add reading from register 3. And a bunch of independent instructions. The blue ones are basically independents of these two instructions, whereas this add is red. It's dependent on the previous instruction. In an in-order pipeline, it doesn't have to be this design, but any design, these two pieces of code have something in common. What is that? I guess I'm giving you the answer by just showing that it's red, right? Basically, this add stalls the pipeline, right? It doesn't matter what previous instructions are here or what future instructions are here. Whenever you decode this add, you figure out that this add is dependent on this multiply, and we're presuming that multiply takes long, of course, and maybe load takes long. This add needs to stop or wait until this multiply produces its value. Similarly, this add needs to stall until this load produces its value. And all of these instructions that are independent, that are in blue, you can see that they're independent. They're not sourcing register 3 at all, right? Well, I guess this one is, right? Maybe this should have in blue, huh? Okay, I'll have to fix that. I'm not going to use this code again, so let's do it right now. Pick your favorite register. 9. There you go. Now they're independent. This is called online patching of errors. Processors do this too. Okay. These are basically independent. You cannot execute, right? Basically, first add stalls the whole pipeline. Add cannot dispatch because its source registers are unavailable, right? Actually, its one source register is unavailable. And later independent instructions cannot execute, which is kind of a waste of time, right? You're basically waiting. You could be waiting for maybe 8 cycles over here. But one difference between these two codes is, yes?
I was going to say, I don't know if you care about this, but there's also a dependency with R5.
Oh, that's right, yes. Well, I guess that's true. They don't have to be completely independent. If you want to do that, I agree. How about this? Now that'll make them completely independent of each other too. But I don't know what happened over here. Is this my fault? Oh, I see what happened. Okay, now they're completely independent. Okay, so, but there's a difference between these two codes, right? And we've discussed this before, so I'm going to go over this quickly. Load latency is variable. Right? Sometimes this could be 1 cycle, sometimes this could be 500 cycles, unknown at compile time. Whereas this latency, again, this latency could be variable too, depending on the design, right? If you're multiplying with 0 or 1. So this is not a great example in that sense. But basically, if you have variable latency, it's very hard to, so if you have fixed latency, let's say this was a fixed latency operation, compiler could have a shot at scheduling instructions, right? If this was, let's say, 3 cycles, the compiler could put these operations right before add. Okay. Because these are completely independent. Good, I don't have a register 3 written over here. Does that make sense? So if this was completely non-variable latency, fixed latency, compiler could schedule these instructions before and overlap the latency of the multiply with the latency of these instructions. That way, this add wouldn't need to stall the pipeline. Whereas with the load, it's very difficult to do that, because load may take maybe 2 cycles if it's a cache hit, and maybe 500 cycles if it's a cache miss. It's difficult to schedule these operations. Right. Okay? So it's difficult to tolerate this low latency. Which means that for variable latency operations, we need something to tolerate the latency. And out-of-order execution actually becomes much more effective if you have variable latency operations like that. Because compiler has a shot at scheduling operations such that you don't stall over here. But we know the downsides of that too, right? Because you may not be able to find independent instructions to cover all of the latency, as we've discussed. Okay, so basically, the problem that's common over here is the first add stalls the whole pipeline. We'd like to prevent that, because this wastes performance. So how do you do that? This is what we've covered with data dependencies, right? We've already seen 3 versions of preventing dispatch stalls. Basically, whenever you have a dependency, the instruction that you're trying to decode or dispatch it has a dependency on a previous instruction you stole. Do you guys remember 3 solutions?
Data forwarding.
Yes, data forwarding helps that, but it doesn't perfectly prevent that, right? It doesn't perfectly eliminate that. Eliminate all cases. You're right. It's a way of handling data dependencies, but it cannot eliminate all cases. Yes.
Fine-grained multi-threading with
Excellent.
the correct number of threads.
Fine-grained multi-threading. I don't know if this will show all of them. If I click, fine-grained multi-threading is 1. You can perfectly get rid of all the data dependencies that way. You don't need to stall dispatch. What else? We already covered one of them. I'll give it to you. Static instruction scheduling, right? Basically, compiler somehow ensures that you don't have a data dependency. Well, a data dependency does not stall the pipeline. You don't have a dispatch stall. Yes.
I was going to say dynamic, but we haven't seen it, so.
Yes, we haven't seen it. That's right. There's one more we've discussed, which is.
Isn't doing something else the same thing as fine-grained?
Yes, that's right.
Okay.
I would consider that doing the same thing as multi-threading, which is guessing, right? Which is value prediction, basically. You predict the value of the register. So in this case, for example, you can predict the value that's going to be produced by R3 and keep going. And then eventually you'll need to verify, of course. But you prevent the dispatch and all that. Okay. But these all have shortcomings, as we've discussed. I'm not going to go over them again, but you can think about them. Fine-grained multi-threading, for example, if you don't have enough threads, well, too bad, you're wasted. You're not improving single-thread performance, right? Value prediction, you need to verify, so there's a lot of complexity, and you may be incorrect, right? If you're incorrect, then you need to recover, and you lose performance, actually. Compile time instructions, scheduling, and reordering, we may not actually be able to do that with compile time, for the reasons that we discussed earlier. So we'd like to have a solution that prevents dispatch stalls without the disadvantages of all of these. And the basic idea we've already seen before. The basic idea is data flow, right? The extreme case. In a data flow model, we fetch and fire an instruction when its inputs are ready. In that case, you don't have any dispatch stalls. You just fetch the instruction whose inputs are available. Basically, the problem that we see is really in-order dispatch, right? The problem is really with the control flow model. We have an in-order program order dispatch of instructions. So we'd like to get rid of that somehow, while preserving the nice sequential semantics of the programming. So if the problem is in order scheduling or execution, I'll call dispatch as scheduling or execution in this case. And the solution is really, if you schedule the instruction, dispatch the instruction out of order, then you could get rid of this. Right? If you could somehow do this in hardware without exposing this to the programmer, you can get rid of all of the dispatch stalls. Okay? So how do we do that? And the basic idea of out of order execution is, if you see a dependent instruction, don't just stall the pipeline. Move that dependent instruction out of the way. Keep it somewhere else until its inputs are ready. It's like data flow now, right? Basically, keep it out of the way of the independent ones. You can think of this as move it to a rest area, right? If you're driving on the highway, don't just stop in the middle of the highway. If you need to stop for some reason, right? Go to a rest area. You go out of the highway, right? Whereas in an in-order pipeline, if you're in the middle of the highway, if you need to stall for a dependency, you just stall everyone else behind you, right? I think that's a good analogy. So reservation stations, we'll call them reservation stations. It's not the greatest name. But when an instruction is dependent, or actually all instructions go into the reservation stations. These are places where dependent instructions wait for their values to become available. Okay? That's the main idea of out of order execution actually. Everything else is to support this. Okay. While the instructions are waiting, monitor the source values of each instruction in the resting area. Because once you move the instructions into some place, you enable other instructions to come in. And the idea is, we'd like to schedule the instructions whenever their values, sources are available. Right? That's the idea of data flow. And in this rest area, in the reservation stations, what we're going to do is we're going to keep track of the source values of each instruction. And whenever someone produces a source value, we're going to say this source value is available. And whenever some other instruction produces the other source value, we're going to say this source value is available. And when all source values of an instruction are available, the instruction can now fire. And the hardware will dispatch the instruction. We're going to put enough logic to do all of this. Does that make sense? That's the idea of out of order execution. Instructions are now dispatched in data flow order, right? Because of this, basically. You put all the instructions into the reservation stations, and whenever instructions become ready, or whenever source values become ready, they get dispatched to a functional unit. And this happens in data flow order, not control flow order. Okay? The benefit is, now you have latency tolerance. Your independent instructions can execute and complete in the presence of a low latency operation. Right? And dependent instructions wait in the reservation stations. Make sense? It's kind of a beautiful concept, right? Okay, let me show you the benefit, and we'll go into detail. Actually, we'll cover a detailed example of how this works. So, what is the benefit? If you have in-order dispatch and precise exceptions, I guess this ugly code over here that I corrected before now has changed. But that's okay. You can look at this code. Now these three are not completely independent of each other. But if you look at in-order dispatch plus precise exceptions, over here, everything is committed in order. This is what you get, assuming a 4-cycle multiply, I think, and a 1-cycle add. Is that true? Yeah, something like that. Okay. Basically, dependent instructions stall the pipeline. So this is what you have. This instruction is dependent on the multiply, so it stalls the pipeline. Even though this other instruction is independent of the add, it cannot be decoded. So this needs to stall also. And later on over here, this instruction is dependent on the previous instruction, and it needs to stall for the multiply to complete. Okay? I might have made a mistake over here. This is 5 of these execute for some reason. Okay. Anyway, with an out-of-order execution processor, what happens is this instruction, instead of stalling the pipeline, gets put into the reservation station, so it waits. So if you look at over here, the stall is converted to a wait. And now this instruction can move on, because this second add that's dependent on the multiply is waiting in a rest area in the reservation station. This instruction can move on because it's independent of both of them. And this instruction executes right after that one. This instruction needs to wait because it's dependent on the multiply. Make sense? So the benefit is, you will take a couple of cycles here. I don't. This doesn't seem to be correct over here. But this takes 16 cycles, and this takes 12 cycles. And this is one cycle less than this takes 15 cycles. Curious now, why are there 5 over here? Can anybody guess? It's just a mistake. The multiply over here is 4 cycles.
The first one could be wrong.
Oh, the first one you mean? Oh, I see. No, but consistency reasons, these are 4 cycles, right?
Well, so the multiply doesn't necessarily always take the same number of cycles.
Okay, excellent.
Because I know in ARM, like, depending on if the top 24 bits of the second operand are all zeros, then it takes only like 2 cycles. But if only the top 16 bits are zeros, then it takes more cycles.
That's right. That's not what I intended, but that's a very good explanation for this mistake over here. I like that. That was not my intent. But okay, you got the idea, right? Basically, the dependent instructions do not stall the pipeline for independent instructions. Okay. And we're going to enable that. So how do we enable that? There are 4 key components to enabling out-of-order execution. First is, somehow, you need to ensure instructions get their correct operands, right? Correct source values. Which means that you need to link the consumer of a value to the producer. Some instruction consumes the value, some instruction produces the value. You can think of dependent instructions that way. And they don't communicate through the register file anymore, because the instruction doesn't wait. It goes into the reservation station. It waits somewhere else. So somehow you need to link those instructions. And the idea is the register renaming over here. We'll get to that. You need to buffer the instructions until they're ready to execute. And we'll do this with the reservation stations. And instructions need to keep track of readiness of their source values. Right? Obviously, so that they can fire or they can execute. They can be dispatched when they're ready. And when all source values of an instruction are ready, they need to be dispatched to the functional unit. If you satisfy all of these 4 things, then you enable out-of-order execution. So how do we satisfy these? The first one, how do you link the consumer of a value to the producer? You've actually kind of seen this, right, with the register rename. Remember, with the reorder buffer, what we had was you associate the architectural register ID to a reorder buffer entry ID. That's essentially register renaming, right? You're basically saying this register will be produced by this instruction at this reorder buffer entry. That's renaming. Associate a tag with each data value. Actually, that tag can be arbitrary. It doesn't have to be reorder buffer ID. Reorder buffer ID is actually convenient. But you can arbitrarily generate a tag as long as you're consistent. Right? Okay, and we'll see how it's done. You need to buffer instructions until they're ready to execute. And this is done using reservation stations. Basically, after renaming, each instruction is inserted into the reservation stations. We'll take a look at that. How do you actually keep track of the readiness of source values? Basically, when an instruction produces its value, it broadcasts a tag associated with the value. Now, we don't have registers. Like architecture registers, as you know, are just one way of communicating values now. Now we're assigning tags to values. And that tag is assigned with the register rename. So when an instruction produces its value, it broadcasts its tag, such that all instructions linked to that tag can capture that value, saying that, oh, I'm waiting for this tag. So let me take that value that's produced by this instruction. Make sense? And instructions, obviously, that are waiting in the reservation stations, they compare their source tags to the broadcast tag. And if there's a match, the source value becomes ready, and you capture the source value. It's all done by this register renaming, because you've associated a tag with each data value. And once an instruction becomes ready, the instruction wakes up. Right? How does it become ready? If all sources are ready. And once it wakes up, well, you need to send it to the function unit. But if multiple instructions are awake, you need to select between them, right? If you have one functional unit, let's say one add, but multiple instructions wake up at the same time, you have a choice. You need to arbitrate. And this could happen, right? If you're firing instructions in data flow order, if you broadcast a tag, then many instructions may wake up at the same time. You need to handle this case. Okay? So that's basically out-of-order execution, conceptually, if you will. Linking of the consumer of a value to the producer, buffering of the instructions until they're ready to execute, keeping track of the readiness of the source values of the instructions, and waking up instructions and dispatching them into the functional units when the source values of the instruction is ready. Okay, this is actually the same as Tomasulo's algorithm. This entire thing is invented by Robert Tomasulo, who was an IBM engineer. And this was first used in IBM 36091 floating point units. And there's a nice paper explaining that. The terminology is a little bit old, but this paper explains this concept. I'm not going to ask you to read this paper. I've already given you an overview paper. What's the major difference today? This is just before we cover this. The major difference we have today is this processor did not have precise exceptions. This processor actually had imprecise exceptions. It did have auto-order execution exactly the way I described it, and exactly the way we're going to cover in more detail, but it didn't have precise exceptions. So what happened is, it was very difficult to debug. As a result, even though it was a very fast supercomputer in the 60s, auto-order execution didn't become popular until precise exceptions were added to auto-order execution. And these were two seminal papers that added precise exceptions to auto-order execution. And the first major processor that actually used something very similar to what I just described was Pentium Pro. And actually, MDK5 would follow right after that, I think. And today, most major processors, and I should say high-performance processors, actually use auto-order execution in a very similar way that we've discussed. I'll describe this more conceptually to you. This is a more conceptual way. How we implement this is a separate issue. Today's processors are extremely efficient in implementing this. So they try to minimize those tag matches, right? If you, well, you'll see that there's a tag match process. You can imagine that, right? Because if you're waiting for a tag, and somebody's broadcasting the tag, you need to match those tags. That's a complicated operation. Okay, so let's take a look at what auto-order execution looks like. Basically, you fetch instructions in order, and you put them into this reservation stations. I call this the scheduling logic over here, which we're going to cover in more detail. And the instructions get dispatched into the functional units in data flow order. These are the reservation stations. It's also called the scheduling window. Basically, the window of instructions that need to be scheduled or dispatched into the functional units. And once an instruction finishes execution, it broadcasts its tag and value. And it basically sets the ready bit of the tags over here that match. And we're going to see that in more detail. And later, instructions complete in some out of order, right? So dispatching is out of order, completion is out of order, and they get reordered. So we still have a reorder buffer, and you can have all of the other solutions that we discussed. Yes?
Sorry, I've always been confused by this diagram. Is this like a superscalar processor, and all of those enter the execute at the same time, or is that time going down?
No. These are different functional units. So in this case, I show a single scalar processor. You basically fetch an instruction, but they could go to the add, could go to the multiply.
But it's not all of them at the
exactly.
same time.
Well, all of them could be at the same time, but not at the same.
Not the same stage.
Same cycle, exactly. Not at the same stage. That's perfect. Yeah, if you the first time I used this diagram, it was in the precise exceptions lecture, and it's basically a multi-cycle execute, but single fetch, single instruction fetch pipeline. It's good that you're clarifying it. But out-of-order execution is actually orthogonal to scalar versus superscalar. Okay, so this is the reorder buffer. This is the same thing that we discussed. Basically, you need to reorder instructions such that precise state is maintained and you maintain sequential semantics. So some terminology, this is called the scheduling window or reservation stations, and this is called the instruction window. instruction window contains all of the instructions. Remember, reorder buffer contains all of the instructions that are decoded, but not yet retired. So it contains more instructions than this one, right? Because this one contains all of the instructions that are not yet scheduled. That are decoded, but not yet scheduled. Here, an instruction may finish, so it may not be here, but it may be over here. Okay? Okay, so this is from your reading. Again, I'm not going to go through this, but hopefully you're reading that reading. That reading will enable you to understand things much better. Okay. And this was Tomasulo's machine. So we're going to emulate something like this in this lecture. We're not going to look at the memory, but we're going to look at the floating point functional units. Okay, you remember register renaming, right? Do I need to cover that again? This is a key enabler of auto order execution. And basically it eliminates, it serves two functions actually. Before, this is a slide from the past lectures just to make sure that it's familiar. But basically it does two things. It eliminates output and anti-dependencies or false dependencies. And it also links the values to a tag, right? Basically, output and anti-dependencies are not true dependencies. By renaming the register ID to a reservation station entry ID, as we will see soon, you can eliminate anti and output dependencies. Does that make sense? You covered this with the reorder buffer. You can think of this as mapping an architectural register ID to a physical register ID. And after renaming, once you've done this renaming, this register reservation station entry ID is used to refer to that register. Actually, to be more correct, it's used to refer to that value itself. Because registers are locations that house values that are to be communicated between instructions. We covered this very, very early on in data flow. Basically, that reservation station entry ID is used to refer to that value that's to be communicated. And that value is what links to instructions. Okay? And this whole process eliminates anti and output dependencies. And we've already discussed that. It approximates the performance effect of a large number of registers, even though ISA is a small number. And we'll see that. Now we can actually have a huge number of reservation stations and a small number of registers. For example, in x86 ISA, there was a time where we had 8 registers, whereas Pentium 4 had 40 entry reservation stations. So if you kept writing to the same register, you could actually have many instructions that are writing to the same register, and they could be communicating with each other. Yes.
Is the size of those total reservation stations proportional to the deepness of the pipeline, such that you can essentially have a different reference for each possible instruction at each possible stage?
That's certainly possible. Yes, it's well. We'll see how a reservation station is organized. It doesn't reference the stages.
I meant no, such that each, I guess. Oh, I see what you're saying. Okay.
But yes, if your pipeline is deeper, it's likely that you need to have more instructions in the pipeline. Because let's say your pipeline is 20 deep, you're fetching 1 instruction per cycle. You need to support at least 20 entry. Maybe not reservation state, certainly 20 entry reorder buffer, right? If your pipeline after decode is that long. Okay. Okay, so let's take a look at how this works. I'll give you an example, but how do you actually do the renaming? This I've shown you earlier. It's done through something called a register rename type table. It's also called a register alias table. Basically, it's a register file. If you remember my terminology from the future file, this is the front-end register file. Basically, at the front end, we had a back-end register file and a front-end register file. Back-end register file contained the architectural state. Front-end register file is a register file that sits at the decode stage. And it's kind of a future file. Right? A future file looked like this, if you remember that lecture. Basically, you fetch instructions, and you decode them, and then they access the register file. At this point, they need to get renamed. And the register file looks like this, whether the register is valid. If the register is valid, what's its value? If the register is invalid, what's the tag that's producing that value, that's going to produce that value? Okay? And this tag, in the examples that we will see, it could be anything actually. It could be assigned in different ways, but we're going to use the reservation station ID. because we're going to put the instructions to reservation stations. If the register is not valid, that means that there is some instruction that's going to write to that register. Now we don't care about the value, but that instruction that's going to write to that register resides in the reservation station ID that's indicated over here. Make sense? This is how you can find that register that's being read at this point in time by this instruction that's in the decode stage. So that's how we'll enable rename. This is the register rename table, or register alias table. So how does Tomasulo algorithm work? I'll briefly describe this, and then we'll go into an example. Basically, we said that when you decode an instruction, you need to place that into a reservation station. First, you need to check if there's a reservation station available. If not, then you need to stop. If a reservation station is available, if you design your pipeline well, and if your latencies are nice, hopefully this is a common case, you take the instruction and the renamed operands and insert them into the reservation station. And we'll see the reservation station structure. Actually, the reservation station structure will look very similar to this. But while in the reservation station, each instruction watches the bus for tag of its sources. There's a bus where the tag and value are broadcast. It's called the common data bus. This is one implementation. Actually, we'll see that there are multiple buses. There could be multiple buses. When the instruction sees a tag, there's logic that basically checks whether the broadcast tag is the same as the tag that is here and that is stored in the reservation station. The instruction grabs the value for the source and keeps it in the reservation station. And when both operands are available, the instruction is ready to be dispatched. And the instruction is dispatched to the functional unit when it's ready. And again, there could be multiple instructions that need to be dispatched to the functional unit. There needs to be a selection logic. Now, after the instruction finishes in the functional unit, it arbitrates for this common data bus. Again, if you have multiple buses, this may not be a problem, but we'll see the problem with the multiple data buses. It puts the tag value onto the common data bus. Basically, it broadcasts its tag as well as the value. And any place in the machine that is waiting for the tag captures the value and sets the valid bit. Now, what do I mean by that? Basically, there could be this tag and value are broadcast to the register file. They're also broadcast to the reservation stations, which we will see now. Okay? Basically, any instruction that's waiting for that tag captures the value, and we've already discussed this. Okay? And at the end, you can actually reclaim the rename tag depending on how you do the rename. Yeah, let's do this exercise. I think everything will become much more clear once we actually emulate the behavior of a machine that does this. Would that be interesting for everyone? Okay. So this is the code that I'm going to go over. And we're going to assume that this is the structure of the pipeline. Fetch, decode, execute, write back. Write back may not be really needed, but we'll see that. We're going to assume that add takes 4 cycles to execute. Basically, E stage is really E1, E2, E3, E4. 4 E's. And multiply will take 6 cycles to execute. 6 E's. And we're going to assume one adder and multiply. And there's several things that we're going to cover, although I'm going to breeze through some of these. How many cycles does this take in a non-pipeline machine? Well, I'm going to let you figure that out, because it's easy. You can actually do that relatively easily. If you take, let's do that. Multiply takes 1, 2, 8, 9 cycles. And add takes 1, 2, 6, 7 cycles. And you have 1, 2, 3, 4 adds. 4 times 7, 28 cycles. And then 2 multiplies. 9 times 2, 18 cycles. So that's 46 cycles, right? If I'm correct. Yes? 46. Good. Yes?
So when you say non-pipeline, you don't necessarily mean single cycle. You mean still have the different stages.
Exactly. Still have, yeah. I should have said, I guess, this is not the pipeline structure, this is the machine structure.
Okay.
Yes, that's right. If it's single cycle, then I have no idea. With the given information. How long it'll take. That's a good catch. Okay, how about an in-order dispatch pipeline machine with imprecise exceptions? I'm going to assume imprecise exceptions for now. That won't change a whole lot. With no forwarding and full forwarding. Well, you can think about this, but this is what it actually looks like. This is with my hand drawing. That's the best way of drawing, as someone mentioned last time. But this is what it takes, basically. Basically, no forwarding. This is the second instruction is dependent on the first instruction, so actually you need to wait until you need to wait for the first instruction to write back until you decode the second instruction. So that's basically a lot of waste, right? It takes 31 cycles. So that brings you from 46 to 31. That's a good jump. If you actually do the forwarding, this is the next one, actually full forwarding, this is the next machine, we can actually reduce that to 25 cycles. So you're improving performance as you go along. What about an out-of-order machine with Tomasulo's algorithm and full forwarding? So I'll show you that this algorithm actually takes 20 cycles. So you can actually improve performance, in this case, by 20%. At least number of cycles by 20%. How? If you look at this code, this is the timeline of all of these instructions, 1, 2, 3, 4, 5, 6 instructions. And in this machine, in-order machine, as we've discussed, even though the third instruction is independent, it needs to wait, because this instruction is in the way. Whereas in the out-of-order machine, while this instruction is waiting, this instruction can execute. This instruction can also execute. And that brings down the number of cycles to 20. Let's take a look at how that happens. You guys want to take a break before we do that? Okay, let's do a short break. How about 3 minutes? Good. 1:33 is good time. Is a good time to come back.
A big issue.
Oh, it's not a. It's just. I think it's an actual name.
Yeah, it's not a big deal. If you collaborate or work with someone,
So
it might be a good topic.
okay. If you were like legit looking.
Yeah, maybe
Friday. Sure.
Thanks.
No, like, this one is sort of legit. This is obviously about to smash everyone's
Still, it's just
I know,
the
he
lighting
does.
is really
And he's
good.
got the weird mustache. And, like,
现在假如这一张作业都做不到了，用个 lab 做，然后我就想到我这，但是 lab
How? What are you up to right now?
这次作业可能是
I'm in 447.
上次有了是吧？
No, but you know.
复杂。
Like in your.
别抄答案，都没怎么过，我们
Like, contemplating it.
这考试我觉得基本上没多长时间。
Not many actual signs. I'm really just gonna like shove a bunch of registers in there and like the way the signatures and stuff.
Yeah, I know that it seems that simple. There's a lot of intricacies.
What?
Maybe I'm just
Possibly.
meaning with using leaders.
I mean, crossplay.
我操，那你多少好好学？
Was it your first
上面
one?
做一些跟你开始搞。
Oh, dude, we have 7 of them.
然后他们50点的在我面密有些，反正每门课那个都有。
我还好，我那个
So that'd be deadly. You would have to use them evenly. I would have to use 3 and 3 because right? Because otherwise you just lose 3 days from the other one.
哎，你里边
Yes.
哦，你当时
That's
都有
not good.
单周，但不是20个小时之内3年
I mean, you could just use all 7 for the last one and then just like
我
turn
操，这
it.
个单是上午3个小时做
But I have to
40
graduate.
3个小时。
反正这两个挨着管，大伙一个挨个在忙。
Wait. These
这其实也
stories
挺好
right
玩
now.
的，看大家
而且会好好。
Like, I wish I just knew. Like, I know I just had because it's like bad. And then like teacher also has mercy calls, so it wasn't
你不是说温总？哦，你说是考试前的那个周吗？你那些人最好玩的是考试名字。
觉得我们这个最好。
除了你之外，没有人知道吗？
搞是个购物车，就是它那个车上有个RFID 显示，你把东西往里一放，这就能知道你东西是啥。就是你到结账的时候，
像那个条形码似的。
不是条形码 ，RFID，
What's that?
就是那20型
Is there food out there? What is that?
它是
Oh, it's your Pop Tart.
它这有个 tag 嘛，就是你只要周围有一个那个买就是你不用扫，不用对着，就在附近。你像那个 ID 卡，
I'm hungry now.
就你交钱之前就知道多少钱吗？
有个人很屌，是跟一个那个 SAE 的那个赛车的那个队合作，就是 CMU 有个赛车队，做那种1级包是有赛车的，就不是真1级包，但是给他一个赛车，然后他给车设计一个什么变态的什么控制系统，据说挺屌的，那车我不好用了。
其实在错，我们里面有一组搞的是那种，就是研究比赛 play track，就跟那个 BBC 看完球赛之后会分析那个人的
但是通过图像处理吗？
对，他那个应该是哪去？
那没有意义，他这样已经他在鞋里装了一个那个就全部
那玩意儿很贵嘛，而且说是如果是高中的比赛或者什么，
我操，那不是100块钱吗？
Real?
你每个人签都
就
I
5
was
个人
like,
呗。
pretty sure you
就
don't
10个人呗，你自己队就准备5万块钱，我咋还谈不起啊？
高中比赛你想就这个。
Yeah.
关键是不是他这个踹个不光是踹个人的那个轨迹，还踹就是他哪个动作，比如手是怎么动，脚是怎么动。
就是
好吧。其实还行，没那么难。熊的那个门课现在做的类似这个，
怎么做的？
就是你人设 video，他把那个人接出来，然后把他那个背景给换掉。
想直接把人弄出来。
What are you trying to change?
To pull up the screen on it. Power it off. If you get independent control over there, right?
No, I think that's for the
Shades, right? I want to power it off.
我知道有个办法可以把人切
What
出
is
来。
there?
对，比如说，假如你的背景固定不动的，
你做 backup subtraction，
对，就把人给做
对，
完了。
咱们是一种方法，就你
I guess we'll see.
你看，
Yeah.
Maybe I'll power it off
没有那么
after
容易。
we do this.
Oh, I've never
为什么得
actually.
考虑到那个相机的角度的问题？一般人会上往下比较好看，那如果不上往下比较好，应该真是。
All right, I guess let's get started. I'll power it off when it's necessary. Okay, so basically we're going to discuss how this works, but how you get this timeline to work. But let me first show you what's the register alias table. This is the register alias table that enables renaming. Right? Again, for each architectural register, you have a val bit, a tag, and a value. Tag is the tag of the writer or the producer. And the reservation stations look like this. We're going to assume 2 functional units, as we've discussed, somewhere over here. Yes, 1 adder, 1 multiplier. An add takes 4 cycles to execute, a multiply takes 6 cycles to execute. We're going to assume these reservation stations. Assume that each has 4 entry reservation stations. And this is what the reservation station kind of looks like. I'm not showing everything in a reservation station here, but basically you need to keep track of each sources. This is the reservation station A, B, C, D for each of the adds that could be waiting for execution for this functional unit. And for each source of the adds, you basically have a val bit. Is the source ready? A tag, if the source is not ready, who is it going to be produced by? Which reservation station entry ID is going to produce it by? If the source is ready, what's its value? And the same thing for source 2. And the first thing to realize is this is exactly the same as over here. So when you're renaming an instruction, basically read the source registers, register alias table entries, and basically copy them to the reservation stations. That's the first thing you do. It's very simple, right? You first allocate a reservation station when you rename an instruction or decode an instruction. And then you read the source register values and take their register alias table entries and copy them over here. Because the register alias table entry says exactly the same thing, that you need to link that source register to its producer. If the register is ready, then you have 2 registers, 2 sources that are ready. And the next cycle, you can start executing. Same thing for the multiplier reservation station. Basically, you have these two reservation stations that are named because we're not going to need more. And once you complete execution, you have two buses over here, the tag broadcast and value broadcast. They're broadcast in the same cycle here. Again, I'm going to describe this conceptually, but in real machines, what happens is tag is usually broadcast earlier than the value. And I'll let you think about why, because this enables instructions to be scheduled earlier, and when they get scheduled, they can capture the value and execute. So you basically ensure that the scheduling of an instruction, determination of readiness of an instruction is out of the critical path by broadcasting the tag earlier. And you can do that with operations whose latencies you can determine earlier. Right? Okay. So we're going to look at this code that I've shown you over here. I've copied over here. And I think I'm going to switch to the board. But basically, we're going to treat it cycle by cycle. I guess cycle 0. Do we have a different pen? We do, but it's hiding over there. So this is cycle 0 over here. Cycle 1, cycle 2, cycle 3, 6, 7, 8, 9. I guess I'm going to go until cycle 8, because that's really the interesting part. I guess cycle 8 is where some instructions complete, right? And all instructions are decoded at that point. Okay. And we're going to do what an out-of-order execution machine does to this code. So at cycle 0, this is the state of the register file we're going to assume. We're going to assume all of the registers are valid, and all of the reservation states are invalid. The machine is empty, basically. And these are the initial contents of the register alias table. For simplicity, I guess I'm going to assume 11 registers. And the values are 1 through 11. And the tags, these squiggly means you don't care about the tag, right? Once the register is valid, who cares what's there? Just don't care. Okay, and we're going to see what happens in cycle 2, but I think I'm going to do that on the board. Let's see. How do we do this? Now, because the power is pulling up of the screen is dependent on the power, I guess I'll have to power off everything, unless you know how to do this. Rachada? No. You don't know? Power off is what I want to do then? Oh, well, there you go. This is called false dependence. Two operations that really need to be independent of each other are dependent. I'm going to draw the same machine that I showed in that picture. If you have the slides are online, you can follow through them. Oh. I guess you could project over there. That's a good idea. As long as no one is sitting there. So let me draw things again here. So at cycle 0, we said that we have a register alias table that looks like this. I think I will draw this in full, if you bear with me. Register 1, register 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Can people see this from the back? Yes? No? Can you see it from the very back? Yes? Who says no? Sort of? You can move forward. That's my solution to that problem right now. But basically, these are the values. I'll try to write bigger. But all registers are valid. Okay. And let's make this big also. If the register is valid, well, what did I do? I put the tag first. And then I'll put the value next. So to keep consistent with the handouts as well. All registers are valid, so tags actually do not matter. And the values are assumed to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Nice, right? Okay, let's draw the reservation stations also. I'll stick to this picture over here. Basically, this is the adder functional unit. And you have a broadcast bus, tag, value. Again, we're going to assume tag and value are broadcast at the same time. But to minimize cycle time, to ensure critical path design, they don't have to be. In fact, they're not in existing machines. I'm going to draw the reservation stations this way. Basically, there are 4 reservation stations, A, B, C, and D, for the adder. And divide the sources. For source 1, we have the valid bits, and we have the tag, and we have the value. And for source 2, we have the valid bits, and we have the tag, and then we have the value. And now you can immediately say that, oh, if a reservation station is not allocated, there should be another valid bit, right, for the reservation station itself. I'm not going to show those other control bits. There has to be a valid bit for the reservation station itself. This valid bit means, is source 1 ready? This valid bit means, is source 2 ready? Actually, why not? Let's show the valid bit for the entire reservation station also. We'll kind of do it this way. Although this doesn't appear in your handouts. Is reservation station allocated or in use? Okay? And initially, this is all zeros because there's nothing in the machine. Now let's see if I can fit this. Oh, this can get really messy. And this is a multiplier. Again, you have the tag and the value bus for the multiplier. Basically, we have multiple buses. That's what I'm going to assume. And again, we have 4 reservation stations for the multiplier. Okay. I hope people can see this in the back. And we're going to name only 2 of them because we're not going to make use of the other 2. I guess I will name all of them. X, Y, Z, T. T comes after Z in the alphabet. Okay, this is source 1 for the multiplier, value, tag, and valid tag and value. And this is source 2 for the multiplier, valid, tag, and value. Okay? Now you may wonder where these value and tag buses go. They're actually connected to every single tag and every single value over here. Okay. And when this tag is broadcast, you have a comparator over here comparing that tag to every single one. And you have a mechanism to latch the value. Yes?
So the one from the adder needs to also connect with the multiplier reservation?
Yes, absolutely. Absolutely. That's the complexity of this, right? That's why this is hard to scale, as we will see later. By the way, let me do the values over here. Yeah, is reservation station being used? Yeah, feel free to ask questions. Hopefully everything will become clear. But basically, if you have these separate buses, because a multiply may need a value coming from the adder, right? So this tag bus needs to be connected to every place in the machine, literally, that can wait for that tag. And it needs to be collected to the register file also. If I show these connections, this will become a mess. So I'm not going to show these connections. But as we go through this, you will see that that is the case. Okay, let me get the red one over here. I guess red one is used for changes. So okay, let's look at cycle 0. Well, this is cycle 0. In cycle 1, nothing really interesting happens. Basically, you fetch this instruction. So let's take a look at what happens in cycle 2. We're now decoding this instruction that's a multiply. So the first step, if you look at the, oh, there you go. Thanks, Richa. If you can read that thing over there, but you can watch me also. Basically, the first step is what we're doing, the instruction that we're dealing with in cycle 0 is this multiply. The first step is to have this multiply put into the reservation stations. So how do we do that? Basically, the multiply, the first step is read sources from the rat register alias table. Now multiply sources are R1 and R2, right? Basically R1 and R2. And what do? Basically, well, the first step is actually we want to allocate a reservation station entry for the multiplier. So the logic asks, is there a reservation station entry available? And the answer is yes, basically. On or of these, or won't work, right? And nor of these will give you the result. Okay, basically we allocate reservation station X for the multiplier. And sources are read from the register file or register alias table, and they're placed into that reservation station entry. Basically we copy. I'll write R1 and R2 over here. What do we copy? As source 1, it's valid, its tag is squiggly, and its value is 1. 1, squiggly, 1. For source 2, it's R2, valid, squiggly, 2. Valid, squiggly, 2. And reservation station is now in use. Right? We're not done yet with renaming. Now we're actually taking our sources or renamed our sources. In this case, we link them to the value, right? Because the value is available. We won't wait for any tag because both sources are ready. But we also need to rename the destination register. Second is rename the destination register. This is the decode stage. Actually, the first is allocate a reservation station entry, an appropriate reservation station entry, of course. And we're doing that for the multiplier. We read the source from the register alias table. Now we need to rename the destination register such that any instruction that's going to source that destination register, which is R3, should look for that tag, which is going to produce it. Right? Now it's not going to be in the register file anymore. It's going to be produced by reservation station X, because multiply is being placed in that reservation station X. So what do? Basically, it's multiply makes register 3 invalid, and you don't need to change this, but you don't care about that value anymore. And the value is really going to come from the instruction that has a tag X, or reservation station entry ID X. Make sense? Now any instruction that's going to later source this register 3 is going to look for X. Okay, that's it. Now we renamed multiply. Let's see if that's true. That's right. I'm not missing anything, hopefully. Okay. Now at the end of cycle 2, now this can actually depend on how you implement things. This becomes ready now. You see that this is ready, right? So it's going to start execution. There needs to be some logic that checks whether or not this can execute in the next cycle. I'm not going to tell you exactly how this is done, but you could actually think of designing this depending on what your critical path is. You could do that during this cycle while you're renaming. Now this becomes ready, right? You know that this is ready. So multiply becomes ready to execute at the end of cycle 2. Right? This is your multiply over here. Because why? Because both of its sources in the reservation station that it's placed to are ready. Okay? That's cycle 2. Okay, let's look at cycle 3. Things become more interesting over here. Because multiply is ready, in cycle 3 it can start execution. So we're here right now. It can start execution. Basically it starts execution. But there's another instruction now in the decode stage, which is add R3, R4, R5. Let's take a look at what happens to that. Again, it follows a step. Allocate a reservation station entry for that add. Is there a reservation station entry available? Yes. So now it's allocated. It's allocated to reservation station entry A. Read the sources from the register alias table. The sources are R3 and R4. Now let's take a look at R3 and R4. Well, R3 is invalid. Its tag is X. Its value is squiggly. Invalid, X, squiggly. R4 is valid. Tag is squiggly. Value is 4. Valid, squiggly, value is 4. So now we've got the sources. We've got one source ready, but the other source, now we know where to get it from, right? It's it's not going to come from here anymore. It's going to come from the instruction that basically broadcasts the value, broadcasts the tag x. And who's that instruction? Over here. And when this instruction finishes, this instruction that's dependent on it will capture that tag and the value. Okay, we're not done yet with the renaming of the second instruction. The last thing is to rename the destination register, which is R5. And this means that you write the tag of the ID of the reservation station to the destination register. This destination register becomes invalid now because it's not ready yet. Now this instruction is writing to it. The tag is A, and the value we don't care because it's going to be over. Yes.
I have a question about the valid bit, I guess.
Sure.
Because we're saying that R4 is valid,
Yes.
which means we should get its value from the actual register, right?
Yes.
So,
Which is here.
but did you get that from there, from the rat?
Yes.
So the rat also always has the last, so you don't even have to look at the register, you would always just look at that.
Absolutely.
anyway.
So this is actually a register alias table, but also the values. You can think of this as the register file, an extended register file. So it adds the values. Because at the time you're decoding this instruction, this value is ready. That means that no one in the pipeline is writing to it. This is the value you want. And you basically take that and copy it to the reservation station.
But you still have the backend one, which would be referred to in case anything goes wrong.
Yeah, exactly. Yes, exactly. Exactly. So to support precise exceptions, you need to have a register file that's non-speculative, architecture register file, just like we discussed. I'm not going to show that over here. If we had more time in this lecture, I would have shown you the entire thing with load store buffer, but that'll take a long time. So you'll need to build upon this. Does that make sense to everyone? This is showing the, we could think of this as the future register file that we discussed earlier. Or register alias table. There's another register file that reflects the architectural register state that's updated at commit time in program order. That's different from this. Okay, that's a very good question. Let's see, where were we? We're in cycle 3. And so basically at cycle 3, now we renamed add. Okay? This add, at the end of the cycle, is not ready. Right? It cannot start executing because this instruction is not broadcast its tag yet. Right? So this waits. This will wait until this tag is broadcast. And we'll see when that happens later. Okay? I guess I have a couple of aside over here. What does that say? Yeah, does the tag need to be associated with the reservation station entry of the processor? Well, it actually doesn't, right? In this case, this is just an implementation choice that we made. It could be anything. You don't really need to associate it with the A, B, C, D, X, Y, Z, T. As long as the instruction that's broadcasting its tag knows what to broadcast, and the instruction that's waiting knows what to wait for, and you correctly link them, it doesn't matter. You could, for example, use the reorder buffer entry ID. You could, for example, use something else. Basically, reservation station is a place to hold the instructions while they become ready. Keep that in mind. We're also using the names of the reservation stations as the tag here. But the tag could be something else. Okay? So if you read this, tag is a tag for the value that's communicated, basically. It's a name for the value. And you could generate that name in some other manner. You could have the reorder buffer ID, for example, because we'll still have the reorder buffer. Okay, that's an aside. Let's take a look at cycle 4. We're done with cycle 3. At the end of cycle 3, this add cannot execute. But this multiply is still executing. Let's take a look at cycle 4. Now we can enable, hopefully, the execution of this independent instruction. Let's take a look at how that happens. Well, it's kind of obvious if you're following so far. Now we're going to decode this add instruction that's reading from R2, R6, R7. Again, the first step, allocate a register, a reservation station entry. Is it available? It's available. So allocate reservation station entry B. Then read the sources from the register alias table. Sources are R2 and R6. So we take R2, valid, squiggly, and value is 2. And then we take R6, valid, squiggly, 6, value 6. And immediately we see that this can become ready at the end of the cycle, right? Both of its sources are ready and the values are available for it. Okay, we're not done yet. We're not done yet. We need to rename the destination register for this instruction, which is R7. And basically now we rename R7 to have the tag of the reservation station, right, over here. Simple, right? Basically the tag becomes B because the reservation station B is going to produce that. Okay? Are we done with the cycle? Well, at the end of the cycle, again, now the logic can determine that this instruction can execute. Because both of its sources are ready. And in the next cycle, you can start the execution of this instruction in the adder. And that instruction is R2, R6, R7. This says now, because we've taken this dependent instruction out of the way, this instruction can now execute. That's how out of order execution happens, because this instruction that's out of program order later in the program than this instruction starts execution early. Make sense? And it's all because of this machinery that links the instructions and renames registers. Okay, that's cycle 4. Let's see. Okay. I guess I don't have cycle 5 and 6 over here, but I'll go quickly over that. Now that everyone has gotten the gist of it, hopefully. Is it clear? So, yes?
We assume that you've got multiple adders and multiple multipliers available, right?
No, it's only one adder and one multiplier, but they're pipelines.
Okay.
Yes.
Okay.
Okay? You could have multipliers and multiple multipliers also.
Otherwise, maybe you should be having a bit which says that if the resource is available or not, if it's not pipeline.
That's right, exactly. Yes. Yeah, I'm going to assume that it's pipeline. Although I'm not sure if it matters. Yeah, it does matter here because now you have two adds that are going in a pipeline manner, right? That's a good question too. Okay, so let's look at cycle 5 quickly. Now you've gotten the gist of it, so we'll do it quickly. At cycle 5, these two instructions are still executing while this is starting execution. We're decoding R8, add R8, R9 to place the results into R10. Again, you've gotten the hang of it hopefully. Allocate a reservation station entry, it's an add. Allocate reservation station C. Read sources R8 and R9. One squiggly 8, one squiggly 9. And then rename the destination register, which is R10. So R10 becomes invalid and gets a tag C. And for consistency, I'll make it squiggly also. Okay. And obviously, at the end of this cycle, this instruction becomes ready to execute. Logic dispatches this instruction in the next cycle to the adder. And the adder is pipelined, as you mentioned. Okay, that's cycle 5. Cycle 6, over here. Now you have 3 instructions executing, right? Is that true? Yes. This, and this. They're all executing. Which means I need to have some control bits, perhaps, right, to see that they're executing. Because we need to eventually deallocate this. Okay. And we're decoding multiply R7, R10 into R11. We allocate a reservation station entry for the multiply. So we go to the multiplier, allocate the reservation station Y. Read the sources R7, R10 from the register alias table. R7, 0, B, squiggly. R10, 0, C, squiggly. None of the sources are ready. 0, B, squiggly. 0, C, squiggly. So in this case, this multiply is going to wait for both of its sources to become ready, right? And obviously it cannot be dispatched in the next cycle because it needs to wait. Let's take a look at cycle 7. At the end of cycle 7, well, during cycle 7, these instructions are executing, these 2 instructions are waiting. And you know which instructions are executing, which instructions are waiting, right? The instructions that have their sources ready are executing. The instructions that have at least one source not ready, not valid, are waiting. We're decoding add R5, R11 into R5. Allocate a reservation station entry for the add. Read the sources from the register alias table. R5, R11, 0, A, squiggly, 1, squiggly, 11. 0, A, squiggly, 1, squiggly, 11. Right? And rename the destination register. What is this destination register? It's R5. Well, R5 is invalid. And the instruction that's going to produce this version of R5 is actually in register is actually has a tag of A. So how do we rename it? Well, it's simple. This version of R5 is gone now. Right? When we decode this instruction, now we have a new version of R5. So the new version will really come from D. Right? And we still don't know what the value is. Make sense? And later instructions that are going to reference R5 should get the value from D, not A. That makes sense, right? This is critical. Because this is program order. Any instruction that sources R5 later on should get the value from D, where this instruction is placed, and not, well, not this one, right? This is where we had placed the previous version, the previous instruction that was producing R5. Makes sense? Yes?
What if there's something that was still waiting on the first value?
Doesn't matter. No one is going to wait from here. When that instruction, for example, actually there is an instruction that's waiting for the first one, right? If you look at this, I'll have to figure that out. Because this was A before, right? This instruction is now has the correct tag. It's waiting for A. And when the instruction at A broadcasts its value, this instruction will capture that value. Because it'll see that tag is broadcast. Because we've already linked that instruction. Does that make sense? Later instruction, this is for later instructions. That's why it's called the register renaming table or register alias table. Register rename map. So there are many names for this. Okay? Is this clear to everyone? Okay. Because you already linked those instructions. You could actually write the, what I could do over here is really write the reservation station IDs. So this is really reservation station X, right? And what else? I guess this is easy. A, B, C, D, and this is Y, right? Since I've allocated them all in order. Okay? So now, everything that sources R5 will know to get the value from D. Tag. Okay. So that's why your handout over there says, note what happened to R5. That's what happened. Later instructions will reference that version of R5. Okay, so cycle 8. Now we're reading all of the instructions. This is the status of the machine. Well, let's take a look at what happens at cycle 8. Something interesting happens at cycle 8. Actually, two interesting things happen. This is the last stage of execution. And I'm going to assume that at the last stage of execution, this multiply broadcasts its tag. This is also the last stage of execution for the add. It happens to be. They both happen to complete in the same cycle. So they'll both broadcast their tags. So what does that mean? Let's first take the multiply. So this multiply that's been executing for 6 cycles at X is complete. And its tag is X, which means I need to carry over the tag for the functional unit. Its value, hopefully if the multiplier is corrected, is 1 times 2. Right, 2. Now this tag, because that's the end of execution, gets broadcast to everywhere that has the name tag over here. If I had another pen color, do we have another color?
I'll search.
Okay, if you have something that may be better, then I would do these connections. But this tag gets broadcast to every single location over here. And any instruction that has a value, any source that has a value of 0 and a matching tag, or X, will capture the value. So basically, oh, what happened? Oh, you have one. Thank you. I guess this is. So what does this look like in hardware? Unfortunately, it looks like this. You have basically for each of these locations, you have a bus that goes over everywhere that says tag. So, and then one more over here. Okay. I don't know if you can see that, but basically what is each tag matching logic looks like basically you have the broadcast tag, and you have the tag that's stored here. You check whether they're equal, right? I don't know if this is how you look at it, but basically compare. If the comparator matches says yes, and actually you need to take into account the values, of course, because you don't have squiggly in hardware, unfortunately. Yeah, you have a better one? Thank you. Let me do this again, I guess. Is it much better? I guess it is better.
Could be an X.
But you know that the tag is broadcast everywhere. No, because I've gone through it twice, you know where exactly it goes. Basically, you have a tag matching logic that compares the broadcast tag to the tag that's stored here. And if the source is not valid, and if the tag matches, then the broadcast value, which also goes everywhere where it says value, is latched into the value. Okay? So you have lots of comparators that are comparing the tags. Oh, okay. Let's see if yours works better. You have lots of comparators that are comparing the tags and also the values that are getting matched. This works similarly. Okay, I guess this is the nature of the thing. So where does this match? We're broadcasting X. Let's start from here. Well, in this case, these are not valid. These are valid. And you do actually compare with itself also, right? Either these are valid, so you don't do anything. There's not a tag match that's needed. Here, this is invalid, but the tag doesn't match. This is B, this is broadcasting X. Invalid, but the tag doesn't match, so nothing happens here. This is invalid, it's waiting for X, and the tag that's broadcast is X. Now we have a match, right? Which means that this reservation station captures the value that's being broadcast, which is 2, and makes the source valid, and we don't care about the tag anymore. Right? That's how we got the value. This add that's dependent on multiply gets the value by the broadcast of that tag and the value. Now in the next cycle, cycle 9, this add can start executing, right? Because both of its sources are in. And that's why you see this add can start executing over here. Make sense? And you do the same thing for everywhere over here. Here there's no match. None of these actually these are valid, so it doesn't matter. But this is invalid, but it's waiting for tag A, but the broadcast tag is X, so there's no match. There's one more place. This tag is also broadcast to the register file, because it's also waiting for the register file. Later instructions should get the correct value. So basically all register file entries or register alias table entries compare their tags if the register is invalid to the broadcast tag. In this case, register 3 has a matching tag, right? So what happens? This register 3 becomes now valid. You don't care about the tag anymore, and captures the value that's being broadcast at the same time. And none of the other ones match. Now we have the correct value of register 3. And after this piece of code, you can logically see that there's only one register that's writing to register 3. And the register 3's value should be 2, right? Based on the original context of the register file. Okay? It's clear, right? Now, to make things even more complicated, at the same time, something else is happening. So this is how this instruction gets completed. Now it's completed execution. You can actually do this at this time. Well, basically you can now deallocate its reservation station entry, right? Because you don't need it. This instruction is executed now. And these could be all don't cares. Make sense? Or zeros, depending on how you define it. At the same time, what's happening is also, this add is also broadcasting its value. So this adder's tag is also being broadcast. Which means that that needs to go into everywhere that says tag also, and we need to have separate comparators, right? We need to have two comparisons that's happening for the same tag. Because two things are broadcasting their tags at the same time. Well, I didn't do a great job with these markers, but you can imagine, right? Basically, the tag well, this is not it. Sorry. We're already done with this. This tag gets broadcast everywhere. Or you have a tag. So you have two tag and value broadcast buses. One for the multiplier that we've covered, one for the adder. So what will the adder broadcast? The adder broadcasts, this add, B. B is this one, right? Yes. Basically, the tag that's being broadcast is B, and the result is 8, because you have 2 plus 6. Right? Okay? And you do the same thing, basically. Everywhere that is waiting for a tag, B captures the value, 8. So you have parallel comparisons everywhere. It doesn't happen here but there's one instruction that's waiting for a B over here, which is instruction that's put into reservation station Y. It captures the value, becomes valid, tag becomes squiggly, and the value becomes 8. Now one of its sources is ready, but it still cannot execute because the other source is not ready. Because you cannot start execution cycle 9. And this instruction can now get out of the reservation stations, right? Because it has completed execution. Okay? So you can actually keep going, keep doing this. And you can complete the entire picture over here. I'll let you do that.
I assume it's on homework.
It's what?
I assume it's on.
No, this is not on the homework. But you have much more interesting questions on the homework. A lot of reverse engineering questions. For example, just by looking at this picture, you can construct this code. Right? If you know the concept, it's easy, right? Now you can follow which instructions are dependent on each other, right? The tricky part is this register 5. Who's writing register 5? Right? I'll give you that hint. Just by looking at this picture, I don't give you this part.
Yeah.
You can construct that code. You can construct a data flow graph. Right? In fact, we'll do that in a later slide. But it's fun, right? Because you know exactly which instructions are linked, right? Just by looking at this, for example, well, maybe not this, because now we've gotten rid of some of the instructions. But looking at this, yeah, cycle 7. Because at cycle 7, we renamed all of the instructions and no instruction is completed. Just by looking at this, you know that, I don't see that. First of all, you need to be able to see it to figure out what's happening. You know that, for example, instruction Y is a multiply, because it's a multiply reservation station. It's waiting for instruction in reservation station B, which is an add, and instruction in reservation station C, which is another add. And you know also that, well, hopefully you know that, because no instruction is completed, instruction B is actually adding register 2, because there's only one register that has a value 2. Instruction it's adding register 2 to register 6, right? Because register 6 is a value 6. So you can decode that instruction that way, reverse engineer. Make sense? So you'll probably have an exam question that looks like this, and maybe harder. It's fun. So if you understand how it works, it's actually pretty simple. So you know the instruction C also, right? It's adding register 8 to register 9. And then that means that you know the instruction in Y. It's multiplying. Well, I guess you need to figure out the destinations. How do you figure out the destinations? Basically, you look at the register file. Who is producing, which is, for example, what is the destination of the instruction register in reservation station B? You look at register 7, that is not valid, and it's waiting for the tag B, which means that the instruction in reservation station B must be producing that register. Which means that the destination register of the instruction in reservation station B is register 7, right? So now you've figured out what that instruction is. It's fun. That's how you do hardware debugging sometimes. Okay. Okay, so now you know exactly how auto-word execution works. And you know the complexity of it also, right? So if you have multiple functional units that are broadcasting results at the same time, you need to add more comparators, right? So you have lots of comparators. This is one of the reasons why this is not very efficient. How you actually enlarge the number of reservation stations that you have. The number of comparators increases with the number of reservation stations, It also increases with the number of functional units. So as you make your machine deeper, which requires more reservation stations, as you mentioned earlier, and wider, you need to have more comparators. And that's expensive. And we'll try to fix that problem later on. Okay. So here, I kind of ignored this right stage. Because if you have imprecise exceptions, you need to do the right over here. But if you have precise exceptions, these rights happen later on, right? When you write, you also write to the reorder buffer. And once instructions complete in order, then you write to the register file. So to be completely correct with precise exceptions, you write to the reorder buffer, maybe at the same time here actually. So I'm not going to show that also. Well, actually here you commit it, right? Basically you write to the architectural register file also. Here you write to the architectural register file, and only after you finish this instruction you can write this instruction to the architectural register file. And only after you finish this one you can write this to the register file, architectural register file, and done. Make sense? That's with precise exceptions. And if you want imprecise exceptions, you do the right after things are done. Instructions are done. Okay. Oh, I guess I'm projecting from there. Can you guys see it? We have only a few minutes, so I'll project from over there. Okay. Unless Rachada has a magic switch quick, but that's okay. It'll take some time. Basically, that's the idea. Use a reorder buffer to reorder instructions before committing them to the architectural state. The instruction updates the register alias table when it completes execution, which is the future register file. The instruction updates the architectural register file when it's the oldest in the machine and has completed execution, which is the backend architectural register file that I do not show over. So this register file is used for value communication between instructions, as we've just seen, value and tag communication. And that register file is used for precise exceptions, just like in the in-order machine with multi-cycle execution. Again, we're back to this. Okay, I think let me conclude. Basically, what we've done is, let's revisit this. We've linked the consumer of a value to the producer with register renaming. We've associated a tag with each data value. And that tag accompanies every single place where that data value might exist. We buffered the instructions until they're ready in the reservation stations over here. I'd like to switch between that and that. We buffered them in the reservation stations over here by inserting them into the reservation stations after renaming. You kept track of the readiness of the source values of an instruction. And how did we do that? By associating valid bits with each source value. And we broadcast the tag of a value when the value is produced. And that tag is broadcast everywhere that could be waiting for that tag potentially. And when that tag is broadcast, instructions or the reservation stations and the register file entries that are waiting for that tag capture the value with these comparators that we've discussed. And when all sources of an instruction are ready, now we can dispatch the instruction to the functional unit. Now you've seen that process. But all sources of an instruction must be ready. This is called the wake up and select. Basically, instructions waken up. Well, in this case, we didn't see any cases where you select between multiple instructions that are ready at the same time. That didn't occur, but it could occur. That could be a good example, actually. You could ask you the arbitration policy. You could think about it. Okay. Yeah, let me summarize with the summary of the. Well, there are other details over here. Right? What about an immediate value, for example? Well, immediate value, you can set the valid bit, tag is squiggly, and value just what's the immediate that comes out of the instruction. Right? So this is a very general purpose design. Okay, summary. Basically, with register renaming, we've accomplished two things. We've eliminated false dependencies. We've also enabled the linking of producer to the consumers. With buffering, we've enabled the pipeline to move forward for independent operations. With tag broadcast, we've enabled the communication of the readiness of the produced value between instructions. And with the value broadcast, we've obviously enabled the communication of the value itself, right? And with wake up and select, we've enabled out of order dispatch. We've enabled out of order wake up, right? Okay, I think let's stop here. But maybe you can look at the slides and figure out how you can build the data flow graph from that cycle 7.